what are these time domain specifications? Basically, they are the parameters of the time response of the system. So we take underdamped step response and will define time domain specifications. Generally, for any control system design, underdamped system response is preferred. We will see why it is preferred later, but at this instant we will take the underdamped second order system step response to define some of the time domain specifications. Now these specifications give characteristics of the dynamic system, means especially in a design, when you design the system, we are expected some specification from the customer. Let us say those specifications in terms of rise time, peak time, settling time and peak overshoot. So these are the design specifications, or they are the performance indices of my system. When I say my system is too good or when a system is too bad, it all depends on by looking at the parameters. So how these parameters, how these specifications are. Based on that, we can easily predict the response of the system. Now here we will define those time domain specifications and we will try to derive equation for those time domain specifications. Let us look at your time response. That time response is underdamped response for giving step input. Therefore, the steady state value is 1, and we have oscillations and finally is going to a steady state value. Now, so most of the specifications what we define here are transient specifications, because I am going to look at only the transient part of my this response and I will define. So here itself I can define. So your response is starting from 0 and it is going to be 1. So when the response is going to 1, it is rising, right? I can define the first one is a rise time. So what is the rise time? Rise time is nothing but the time taken by this response to reach the 100% value. What is 100% in this case? 1, right? And it is going to the 100% for the first time I want. So it is going, there are oscillations, so it is going to the steady state value many number of times, but I want at the first time to reach the steady state value, how much time the response is taking. That is the rise time. You can look at here what is the rise time. Similarly, I can define peak time. So your peak time is the time taken by the response to reach the peak of the response the first time. So you can look at here, it is going to the peak. So it is going to the peak at this particular time. Therefore, what is the time that is? It is reaching the peak value. So this is the peak time. Similarly, I can define peak overshoot. So peak overshoot is, we have the steady state value and we have the peak value. What will be the difference? So that difference also important in most of the control system design. And also we can define the settling time. What do you mean by settling? So settling time is something which is the time where the transition takes place. The response means, so it changes from transient to steady state, right? So you can look at here the oscillations slightly are there, and I can define a certain band. Let us say 2% and 5%. The response is reaching to that band. I can say the system is settled. So when you look at any practical system, we expect the response go to the steady state value, but so it will not go to the steady state value. Then it oscillates around the steady state value. So even if it is oscillating around the steady state value, if the oscillation magnitude is very small, we can take it as a steady state response or a steady state value. That means my response is settled down to a steady state value. So we can define it as that time taken by the response to reach and settle within a specified band. That is the settling time. And also we can delay time sometimes. So delay time is time taken to reach the response 50% of the final value. So these are the some of the, you can also say what is the oscillations, time of oscillations, time period of oscillations. The time period of oscillations, you know what is the frequency of oscillation? The frequency of oscillations of your underdamped response is omega d. Therefore, we can define time period of oscillations also. These are the some of the time domain specifications. Let us see one by one how can you get the expressions for those time domain specifications. We'll start with rise time. So we'll have already the response. By looking at the response, and then we'll define and we'll derive. Now, what is the rise time? So it is the time taken by the response to reach the first time the steady state value. Means I know already C of t expression. C of t is equal to 1 minus e power minus zeta omega n t by under root 1 minus zeta square and sine omega dt plus phi. So this is the C of t expression. Now at a time t is equal to tr, tr is the rise time. At a time t is equal to tr, my C of t value should be 1. That is the steady state value. So if you do that, now your C of t is 1. So 1 is equal to 1 minus e power minus zeta omega n tr. In place of t, I will take tr divided by under root 1 minus zeta omega square, 1 minus zeta square and sine omega tr plus phi. So then here I have 1 is equal to 1 minus something. Therefore, this second term obviously is equal to 0. So the second term is your e power zeta omega n tr by under root 1 minus zeta square sine omega d tr plus phi is equal to 0. There are two terms and the product of these two terms is equal to 0. Then when you will get the 0, either first term should be 0 or second term should be 0. Let us look at the first term. When this first term will be 0, this will be 0 when tr value is infinity, because it is e power minus t term. When tr is infinity, this term will be 0. But we are not looking at tr time at infinity, so we are still in the transient period only. So this e power term cannot be 0. Therefore, obviously the second term is 0. So I can write it as a sine omega d tr plus phi is equal to 0. That 0 I can represent as a sine n phi, but I will take n is equal to 1. Then I can cancel sine. Then I can write tr as the phi minus phi divided by omega d. Phi is 3.14 we know. Minus phi is you can define from that damping ratio triangle, either it is cos inverse zeta or tan inverse 1 minus zeta square under root by zeta. You can use any formula to find out the phi. But phi is in radians, but phi should be in radians to match the units. Divided by omega d, you can write as omega n into 1 minus zeta square and the units of it is seconds. Then what I can say finally, your expression for rise time is tr is equal to phi minus phi divided by omega n into 1 minus zeta square under root. This is the expression of underdamped system where we defined the variation of the response from 0% to 100%. Sometimes we are interested to take the rise time for underdamped, overdamped system as well as the critically damped system. For overdamped system, we will take the response from 10% to 90%. It means the time taken by the response to reach from 10 to 90% is the rise time. Similarly, for critically damped, so we can define for 5% to 95%. The time taken by the response to reach from 5% to 95% is my rise time for critically damped system.